Application of reduction formula. Question number 1. 0 to infinity dx upon 1 plus x square whole power n. Let x equal to tan theta, dx equal to sec square theta d theta. We change the limits. When x equal to 0, theta will be 0. When x equal to infinity, then theta will be 90 degrees or pi by 2. We put this value here. Suppose the function is I, 0 to pi by 2. This is sec square theta d theta divided by, this will become sec power 2n because this is sec square theta power n. Sec power 2n theta. So we can write it 0 to pi by 2 cos power 2n theta into 1 upon cos square theta d theta, which will give 0 to pi by 2 cos power 2n minus 2 theta d theta. Now we can apply Wallis formula. This is even function. So 0 to pi by 2 cos power nx dx. For even function, it is n minus 1 upon n into n minus 3 upon n minus 2 dot dot dot, then 1 by 2 into pi by 2. So that thing we can apply here. So this will become I equals, here maximum power is 2n minus 2. So this will become 2n minus 3 divided by 2n minus 2 into 2n minus 5 divided by 2n minus 4 dot dot dot, then 3, then 3 by 4, then 1 by 2, then 5 by 2. And that is our answer. Now consider next question. Question number 2. We are given un equal to 0 to pi by 2 theta sine power n theta d theta. We have to prove that un is equal to n minus 1 upon n times un minus 2 plus 1 upon n square. And after that, one more result is to be derived, and that is u5 is equal to 149 divided by 225. Let's see how. So we can start from here. So un is equal to 0 to pi by 2 theta sine n minus 1 theta times sine theta d theta. We can take this integrable, this as differentiable. So un will be equal to theta sine n minus 1 theta. This will give minus cos theta. It's integration, minus integration of differentiation of these two terms. We can apply product rule. So differentiation of theta into sine n minus 1 theta as it is. Sorry, differentiation of theta we can write as 1 here, 1 into sine n minus 1 theta, then differentiation of sine n minus 1 theta. So plus theta times n minus 1 sine power n minus 2 theta into differentiation of sine theta will give cos theta, and whole times integration of this sine theta will give minus cos theta, then d theta. And limits are 0 to pi by 2. If we put these limits here, so we will get 0. So first term will become 0. Now we are left with here, this minus cos theta is valid for this and for this both. So this will become minus sign, this minus sign will make it plus sign, and then 0 to pi by 2, then sine n minus 1 theta into this cos theta, and then d theta. Then we write second term. So theta, the minus sign here, this minus will make it. This minus minus will become plus, so we will get n minus 1 outside, and then integration. This theta sine power n minus 2 theta into cos theta, and cos theta will become cos square theta d theta. Now, this cos square theta can be written as 1 minus sine square theta. And here, if we put sine theta equal to t cos theta d theta will be dt, then integration of t power n minus 1 will become t power n plus 1, that is sine power n minus 1 plus 1, that is sine n theta, divided by n, and limits 0 to pi by 2, plus this term n minus 1 times integration theta times sine n minus 2 theta times cos square theta d theta. Now further, we simplify it. So this will become 1 upon n plus n minus 1 times 0 to pi by 2. Here limit, I forgot to write, 0 to pi by 2. So then theta times sine n minus 2 theta, and this cos theta can be written as, we will write 1 minus sine square theta. So from there, first term will remain sine power n minus 2 theta, but second term here power n minus 2 and here power 2. So it will become sine n theta. So we can write it as d theta minus n minus 1 this term, and for this, so this will become 0 to pi by 2 and theta sine n theta d theta. Question itself is same, so we can take this term to LHS. So we will get un plus n minus 1, this term u plus n minus 1 un is equal to, here this term can be written as n minus 1 times un minus 2. So 1 upon n plus n minus 1 times un minus 2. Here un 1 plus n minus 1 equal to 1 upon n plus n minus 1 times un minus 2, or un will be equal to 1 upon n square plus n minus 1 upon n times un minus 2. So we have got the result to first part. Now for second part, we have to evaluate u5 equal to 149 divided by 225. So for that purpose, we write u5 1 upon 25 plus 4 upon 5 times u. This will become 5 minus 2, u3. Now we evaluate u3. u3 will be 1 upon 3 square from here, plus 3 minus 1, 2 upon 3. And this will become u1. And we can evaluate u1. u1, if we put here, so this theta sine theta d theta we will get. So this will become 1 upon 9 plus 2 by 3, integration 0 to pi by 2, and theta sine theta d theta. Now we can evaluate it. So let's integrate it first. 0 to pi by 2 theta sine theta d theta. So here we take theta as differentiable function. So theta into minus cos theta, limits 0 to pi by 2, minus differentiation of theta is 1 and minus cos theta d theta 0 to pi by 2. So that will give sine theta, and from where we will get 1 So we can put these values here in this equation. These two will be combined to get the result as U5 equal to 1 upon 25 plus 4 upon 5 times U3, 1 upon 9 plus 2 upon 3 times U1, and the U1 is 1 as we have evaluated here. So this will become 1 upon 25 plus 4 upon 45 plus 8 upon 15. If we simplify, we will get 149 divided by 225. That is our answer. Now, let's see one more question. We are given integration 0 to 1 x power 2n divided by root of 1 minus x square dx. Here, we have to find out the sum of series 1 upon 2n plus 1 plus 1 by 2 times 1 upon 2n plus 3 and so on till infinity. And we have to evaluate this integral. So let's see how to evaluate this integral. Here we put x equal to sine theta. So dx will be cos theta d theta. We can change the limits. When x equal to 0, theta will be 0. When x equal to 1, theta will be pi by 2. So our question will become I equal to 0 to pi by 2. And in place of x, we are going to write sine theta. So here 2n sine power 2n theta divided by, in denominator, we will get cos theta because root of 1 minus sine square theta, and dx will give cos theta d theta. So cos theta will cancel out. And this is even function. We can apply Wallis formula. So from there, we will get 2n upon, maximum power is 2n. So we will get 2n minus 1 divided by 2n into 2n minus 3 divided by 2n minus 2. And last term will be 1 by 2 and then pi by 2. So we have got the value of pi. Now, again, we are going to take another method to evaluate the same. I equal to 0 to 1 x power 2n upon root of 1 minus x square dx. This can be further written as 0 to 1 x power 2n into 1 minus x square power minus half. And we know that 1 plus x power n becomes 1 plus nx plus n minus 1 upon factorial to x square and so on. So the same concept we are going to make use. So I equal to 0 to 1 x power 2n times 1 plus nx. N is minus half and x is minus x square. So this will become 1 by 2 x square plus n into n minus 1. That is 1 by 2 into 3 by 4 and x square. So this will become x power 4 and so on till infinite terms. Now, if we simplify it further by multiplying x power 2n, so what do we get? We will get I equals integration 0 to 1. First term will be x power 2n plus second term will be 1 by 2 x power 2n minus 2 plus third term will be 1 by 2 into 3 by 4 x power 2n minus 4 till infinity times dx. Now, if we integrate it, this is simple question, x power 2n upon power is increased by 1. So 2n plus 1 plus 1 by 2 x power 2n minus 1 upon 2n minus 1 plus 1 by 2 into 3 by 4 into x power 2n minus, here power increased by 1. So one mistake we have done here, power is 2n and this is power 2. So this will become 2n plus 2. Here power is 4, so this will become 2n plus 4. So here we have taken negative sign and that is wrong. So let's rectify it. It should have been positive. So now this will be 2n plus 1. This is already 2n plus 2. So this will become 2n plus 3 upon 2n plus 3. And here 2n plus 4, so one power will increase. So 2n plus 5 divided by 2n plus 5 and so on till infinity. And the limits are 0 to 1. So when we put 0, everything will become 0. But when we put 1, so numerator will become 1. So we will get 1 upon 2n plus 1 plus 1 by 2 into 1 upon 2n plus 3 plus 1 by 2 into 3 by 4 into 1 upon 2n plus 5 and so on. This is I. And we have already evaluated I other way around also this. So both must be equal. So we can write this equal to 1 upon 2n plus 1 plus 1 upon 2 times 1 upon 2n plus 3 plus 1 upon 2 into 3 by 4 into 1 upon 2n plus 5 and so on equal to the previous result. So previous result was this 2n minus 1 upon 2n. So we can write here 2n minus 1 upon 2n multiplied by 2n minus 3 upon 2n minus 2 and so on 1 by 2 into 5 by 2. And that is our answer. Thank you for watching.